Welcome to the fourth lecture. In the last lecture, we talked about transforming the stiffness matrix. Today, we will start with transformation of compliance matrix. So, we can do the transformation in two ways. One is we already know the stiffness matrix in the xy system Q x y. So, if we just invert it, that becomes our compliance matrix in the xy system, or otherwise we can start from the beginning. We can write the compliance relation in the 1-2 system first, and then from there we can define the transformation. So, let us write it in terms of engineering system first, and then we will go to the tensorial definition. So, S11, S12 0, we have S12, S22 0, 0 0 and S66, and this is related to the stresses as this, and this is engineering strain. Now, this same relation, if we change the strengths to tensorial ones, we can write as this, and then S has to be adjusted accordingly. So, in case of Q, for going from engineering to tensorial, we had to multiply Q66 by 2. Here in case of S, we had to divide it by 2. So, this is sigma 1, sigma 2 and sigma 6. Now, here we can put the transformation relation. So, we have T and we have epsilon 1, epsilon 2, epsilon 6 by 2, and we have this same S matrix in the 1-2 system adjusted for tensorial stress definition. So, S matrix multiplied by when we write this transformation relation, if I multiply it by T, this becomes in x y. So, epsilon x, epsilon y, epsilon s. Now, accordingly here we have T multiplied by sigma x, sigma y and sigma s. Now, again we can take T inverse in the right hand side, and we can have a component T inverse multiply by this S matrix with S66 adjusted for tensorial definition into T, and that we can call a new S matrix in the xy system, and then accordingly we can write epsilon x, epsilon y, epsilon s by 2 multiplied by S, S x x, S x y and x x s by 2, and similarly S x y, S y y and S y s by 2, and here we have S x s multiplied by S y s, and then we have x s s by 2, and then we have here sigma x, sigma y and sigma s. Okay, so, all these halves should come here, not in that side, because finally, we want this epsilon s to be 1 by 2. So, this half should not be in those two elements. All right. So, this is our new S matrix in the xy system when our strain is tensorial. Now, if we want to go to the engineering system, we have epsilon x, epsilon y, epsilon s, and accordingly S matrix will look like this: Sxx, Sxy, Sxs, and then we have Sxy, Syy, Sys, and then we have Sxx, Xs, Sys, and Ss, and this is multiplied with sigma x, sigma y, and sigma s. So, this is our compliance relationship in the xy system, and this definition is engineering now. So, again we followed the same approach. We went from engineering to tensorial definition, we applied the transformation rule, and then finally we came back to the engineering definition. Now, S matrix can also be written, I mean we can write the components of S matrix in the xy system in terms of the components of S matrix in the 1-2 system, and these are the relations. Again we see that the xx, yy, xy component and ss, they are all even functions of m and n, which means that when theta changes sign, they do not change any sign. However, the xs and ys components are odd functions, that means when theta changes sign, they also change sign. So, we have transformed the elastic constants. Now, accordingly we can transform the engineering constants also. So, for that let us go back to how we wrote the engineering constants. So, in the 1-2 system we had epsilon 1, epsilon 2, epsilon 6 in terms of the sigmas in 1-2 system as this matrix, and then we multiply this with stress vector sigma 1, sigma 2, sigma 6, and also we have here nu 2 1 by, so this is E 2 and this is E 1. So, nu 2 1 by E 2 is equal to nu 1 2 by E 1. Now, in an analogous way, we can write strengths in the xy system as this multiply, we can define we can write this matrix with similar engineering constants, but in the xy system. So, we have 1 by x 1 minus nu y x by E y, and then we have eta S x by E s. So, we have seen that S matrix has these terms populated. So, there is coupling between the normal and shear components. So, that coupled term we are writing in this way. So, we are introducing a new quantity eta here, that signifies coupling between the normal and shear components, and now here we have nu x y by E x 1 by E y and eta S y by E s, and here we have eta x s by E s, E x, and eta y s by E y and 1 by E s, and this is multiplied with stresses with respect to the x y system. Now, it has to satisfy some constraints. Those are, this matrix has to be symmetric. So, nu y x divided by Ey has to be is equal to nu xy divided by Ex. Similarly, eta xs divided by Ex has to be equal to eta Sx divided by Es, and eta Ys divided by Ey has to be is equal to eta Sy divided by Es. Now, this matrix is nothing but our S matrix in the xy system, and we already know what that matrix is. So, what we can do now is we can equate these quantities 1 by Ex with Sxx, 1 by Ey with Syy, and so on, and use these constants. So, with the help of that we can find out these Ex, Ey and all these engineering constants in the xy system with respect to those constants in the 1-2 system. So, here are the equations that we get. 1 by Ex is equated to Sxx, and Sxx we can write in terms of the engineering constants in the 1-2 system, because we know Sxx in terms of S values in the 1-2 system, and S values in the 1-2 system we know in terms of their engineering constants in the 1-2 system. So, finally, we can write this all these things in the engineering constants in the 1-2 system. So, this is what we get, and after that if we put those conditions, then we get expressions for all these individual engineering constants. So, we have Ex as E1 divided by m to the power 4 multiplied by m square plus m square n square multiplied by E1 by E6 minus 2 nu 1 2 plus n to the power 4 multiplied by the ratio of E1 and E2. Similarly, for E2 here, only thing is that E1 and E2, similarly for Ey here. So, E1 and E2 interchange their position. This is how we get Es in terms of the engineering constant, and here we have a nu Yx in terms of the engineering constants. And if we know nu Yx, we know that nu xy is nothing but nu Yx multiplied by Ex by Ey. Now, again we can see that all these terms are even functions of m and n. So, if theta changes sign, these quantities does not change sign. Now, these are the normal shear coupling terms eta x s and eta y s, and these are odd functions. So, here if theta changes sign, these quantities changes their sign. Now, here we have plotted these quantities with theta. So, we have gone from theta is equal to minus 90 to theta is equal to 90. So, what we see here is, first of all, these quantities are symmetric with respect to theta is equal to 0. That means, the value for theta is equal for theta is same as the value of the value for minus theta, and that is what we have seen, that these functions are even functions of theta. And also obvious thing is that when theta is equal to 0, that means the xy system and 1-2 system coincide with each other. In that case, Ex become E1 because x axis coincide with one axis, and Ey becomes E2. Now, when theta is 90 degree, then x axis match with the axis 2 and y axis coincides with axis 1. So, in that case Ex becomes E2 and Ey becomes E1, and similarly in the negative side also same thing happens when theta is equal to minus 90 degree. Now, let us go to Es. So, Es is also an even function of theta. So, this is theta is equal to 0 line. With respect to this diagram is symmetric in the right and left side, and again we see that when theta is equal to 0, Es is equal to E6, and when theta is equal to 90 degree, again Es and E6 are same, and same is when theta is equal to minus 90 degree. Now, Es has maximum value here when theta is equal to 45 degree. Here also when theta is equal to minus 45 degree, ES has the maximum value. Now, these graphs are plotted by using these values of engineering constants. Now, let us see the variation of nu x y and nu y s. So, this is nu x y when theta is equal to 0, nu x y is equal to nu 1 2 and nu y x is equal to nu 2 1, and both these graphs are symmetric with respect to theta is equal to 0, and when theta is equal to 90 degree, nu x y is equal to nu 2 1 and nu y x is equal to nu 1 2, and these two graphs cross each other when theta is equal to 45 degree and theta is equal to minus 45 degree, which means that at theta is equal to 45 degree and theta is equal to minus 45 degree, nu y x and nu x y are same, and the same thing happens in terms of in the E x and E y also. So, when theta is equal to 45 degree, E x and E y are also equal. Now, let us go to this coupling terms eta x s and eta s x. Now, we have seen that these are odd functions of m and n, odd functions of theta. So, this is antisymmetric with respect to theta is equal to 0. So, whatever value we have for certain theta, for negative theta we have the value just negative of that. So, when theta is equal to 0, both these terms are 0, because we know that when theta is equal to 0, that means the ply is specially orthotropic, 1-2 axis coincide with x y axis. So, in that case no coupling between normal and shear terms exist. So, these coupling coefficients etas are 0. Similarly, when theta is equal to 90 or theta is equal to minus 90, again axis x coincides with axis 2 and axis y coincides with axis 1. So, the coupling term again vanishes, and in between them for any theta the coupling is present. Now, similar features we can notice for the graphs of eta y s and eta s y. Again these are odd functions. So, the graph is antisymmetric with respect to theta is equal to 0, and when theta is equal to 0, theta is equal to 90 and theta is equal to minus 90, due to the same reason that we discussed before, these coupling terms are 0. Now, let us look at just one simple example problem related to this. So, let us suppose that we have a composite ply and the values are not explicitly given, but the ratios are given. So, E 1 by E 2 is equal to 2.8, G 1 by E 2, which we can also write as E 6 by E 2, and that is equal to 0.45, and eta 1 2 is equal to 0.3, and we have been asked to find out nu x y for this case. So, first we have to find out nu 2 1. So, nu 2 1 is equal to nu 1 2 multiplied by E 2 by E 1. Nu 1 2 is given to us 0.3, E 2 by E 1 is just reciprocal of 1 by 2.8. So, multiplied by 1 by 2.8, and the value that we get for this is 0.107. Now, with these values we can find out eta y x first. So, to do this we need to use these ratios E 2 by E 1, which is given here 1 by 2.8, E 2 by E 6, which is given here 1 by 0.45, again E 2 by E 6 and E 2 by E 1, and we know m and n. M and n is 45 degree. So, m is cosine 45 degree, and that is equal to 1 by root 2, and n is equal to sine 45 degree, that is equal to 1 by root 2. So, after putting all the values we get nu y x as this. Now, using this nu y x, if we want to find out nu x y, we can use their relation, and that relation is nu x y is equal to nu y x multiplied by E x divided by E y. So, nu y x we already know, just now we found out, and we need to know the ratio between E x by E y. Now, it is already mentioned that this ply is this is a 45 degree lamina, and we have seen that when theta is equal to 45 degree, if we just look back to this graph that we discussed, at theta is equal to 45 degree, E x and E y become same. That means, the ratio of E x and E y are same, and so it nu x y would become nu y x, and the value would be just what we got 0.29, and that matches with what we see in this graph of nu x y and nu y x also. At theta is equal to 45 degree, the value should be same. If we want to verify that, we can do that. So, for that let us take the ratio between E 2 by E 1. So, if you want to do that, we can find out E x from here, and in this expression E 1 is unknown to me, but these ratios are known to me. So, E 1 by E 6 ratio is not directly known to me, but I can find out the E 1 by E 6 ratio, and for that what I can do is E 1 by E 6 can be written as E 1 by E 2 multiplied by E 2 by E 6. Now, these two ratios are known to me. So, if I multiply that, we get 2.8 by multiplied by 1 by 0.45, and that gives me 6.222. So, E 1 by E 6 is 6.222. So, if I put these values here, now I know everything except E 1 and E 2. So, E x can be evaluated as E 1 divided by 2.36, and E y can be evaluated as E 2 divided by 0.8413. Now, if we want to find out the ratio E x by E y, this turns out to be E 1 divided by 2.36 divided by multiplied by 0.8413 divided by E 2, just the reciprocal of this, and we know the ratio between E 1 and E 2, that is 2.8. So, we have 2.8 divided by 2.36 multiplied by 0.8413, which is found to be 1. So, this is E x by E y. So, our so whatever we saw in the graph, that we verified here numerically also with this example. So, with this I would like to conclude this lecture here. Thank you.